Morning is going to be given by Justin Kasper. Justin is a astrophysicist and heliophysicist in the Solar and Stellar X-ray group in the Astrophysics division of the Harvard-Smithsonian Center for Astrophysics. He's also the winner of the Presidential Early Career Award, which is the highest honor bestowed by the U.S. government for scientists and engineers in their early phase of their career. And he is a member of Jack Burns's Lunar team, which was selected 4 years ago as one of the original NLSI PIs. And his talk is entitled Astrophysics and Heliophysics Supporting Science and Exploration. So, Justin.
Oh, that's terrible.
Yeah,
Yeah.
Interesting.
Yeah.
You're just in time for a talk. Or it's servers.
I can read that. Let me just. No, we're. So was us.
What do you mean?
Okay.
We go to Adobe Connect, and so we can either be them at their end or us at our end as we get it. But I had not seen that
Ever.
ever. Yeah.
I haven't.
So I just assumed it was them. If I'm always nervous to hit a button, because I'm afraid everything will go dark, like DC would just go
So
dark.
someone else has an open mic?
Yeah. Bill Farrell, I think you may have an open mic there.
Okay.
Yep. Thanks.
Justin, mute your Adobe Connect.
Oh, sure.
Go ahead and try that now.
We still hear you via Polycom.
Okay. What about folks online? I'm seeing people saying nothing audible.
Yeah, I'll let the tech folks answer that.
Hey, this is Marco. I just started transmitting from my computer as a backup. Are people hearing this audio?
Sounds perfect. I think that's an affirmative, Marco. Okay. All right. So, Justin, let's go ahead. Yeah, let's go ahead.
Okay. So just for people that didn't hear the last bit, let me just say I'm going to go through some, as those bullets say, topics, selected topics in heliophysics, lunar laser range finding, radio science, and general science enabled by exploration. And if you find any of this interesting, I urge you to listen to session B, where you're going to see more detailed presentations on all these topics. So with heliophysics and space radiation, this is work that I've been doing with Bob McDowell at Goddard, Joe Lazio at JPL, and Jack Burns at Colorado. And for those in the room that are not familiar with heliophysics, you know, our moon and Earth are both influenced by the sun, boring main star sequence halfway through its life. You can see the sun visibly, but also if you look at the real-time display behind me, these are real-time solar dynamics observatory observations of the sun in ultraviolet light. And the sun influences our life and society on Earth and the surface of the moon in ways far beyond just the visible radiation. You have ultraviolet light and X-rays that interact with surfaces and atmospheres. You have energetic particle radiation produced by flares and shocks. And in the field of heliophysics, we're seeking to understand the variability of the sun, how the Earth and objects like the moon respond, and how human activities in those environments are affected. And this is a series of images of the sun on the top of this panel, looking in optical light. And I think there's this is in theory a animation, but maybe it is not rendering right now. So we're able to use today a vast array of different observations using spacecraft such as the NASA Stereo mission, telescopes on Earth, and piece together optically what happens when there's an eruption on the sun. You get a shock wave that can form after a solar flare, you know, massive explosions where, you know, trillions of megatons worth of energy are released in the span of tens of seconds or minutes. And these explosions can produce shock waves that fly out into the heliosphere. And we can image those shock waves now and sometimes watch them traveling all the way out to Earth. But what we can't tell just by seeing the shock itself is whether or not the solar flare, the resulting shock, is going to produce energetic particles. So sometimes, if the physics is set up correctly, and that could involve the strength of magnetic fields, the strength of the shock, its orientation relative to magnetic field and the solar wind, you can get extremely efficient production of energetic particles. And we're very interested from a just basic physics point of view of how particles are accelerated to high energies. But we're also just very interested and keen in being able to develop techniques for predicting whether or not energetic particles are going to be produced by event. If we could predict these events, we could tell astronauts that are undergoing EVAs, that are out on the lunar surface, or that are in the space station to seek shelter before the radiation reaches the moon or the Earth. And one of the techniques we have to tell if particle acceleration is happening is to detect bursts of radiation in low-frequency radio waves that are produced when shocks take off from the solar surface. And it turns out you can actually tell immediately if energetic electrons are being produced by searching for this radio emission. And if you can image it, you can tell where the acceleration is happening. The problem is, far from the sun where the acceleration is really strong, it happens in frequencies that our own ionosphere absorbs. frequencies at 10 megahertz and lower. So if you want to be able to see this particle acceleration as it happens, you need to go into space, either in orbit with a constellation of spacecraft or on the lunar surface. So this is one topic we've been working on, and Bob McDowell has a presentation this morning linking particle acceleration and radio observations. Oh, of course, and now I hit next, and you can see some nice movies of a shock actually playing out. So I'm just gonna let you take in. Here's a sequence of eruptions sweeping out from the sun, heading out into interplanetary space, and you can see those spots all the way out on the right and left are Earth. Okay, let's move on. So Bob will talk, and we have publications on this. We have some simple concepts for a very simple Pathfinder array that we've developed that you could place on the near side of the sun, near side of the moon to observe the sun half of the day. And this would easily enable us to address these basic questions like where is this particle acceleration happening during one of these solar eruptions. Another thing we've been working on, and there are talks on the lunar radiation environment, the deep space radiation environment, all throughout this forum, are measurements of radiation in interplanetary space. So one example of a recent observation that we now have access to is the crater instrument on Lunar Reconnaissance Observatory. So in orbit around the moon, we have 1-second cadence measurements of the deep space radiation environment and how that radiation evolves as a function of distance behind shielding and within a simulation of a human body. This has really transformed our ability to directly measure what the deep space environment would be like. We have observations, and you'll see presentations on this in this forum, not only now of the detailed radiation environment near the moon, but you can actually use these observations and predict what life would be like during a extended journey to an asteroid or a mission out to Mars. I'm just going to move on. So moving from heliophysics, let's look at gravitational physics and lunar laser ranging. And Doug Curry has a presentation on this in detail this morning. I just want to point out here that we already have laid out by Apollo and several Soviet missions retroreflectors on the surface of the moon. By bouncing laser signals from the Earth off of these retroreflectors, we're able to do very detailed models of the lunar interior and how it evolves over time. We're also able to do fundamental tests of general relativity using these lunar laser ranging measurements. And one thing we've been working on, and Doug will talk about this, is advanced laser retroreflectors, more stable, larger surface areas, so you get a stronger signal bouncing back. And we're able to predict now that if we can get these new generation laser retroreflectors on the lunar surface, we'd have a real revolution in our ability to truly pin down both strong tests of general relativity and really advance our ability to study what's going on deep in the lunar core. And Doug talks about this all this morning. A very exciting result that's happened in the last few years as part of the lunar team in NLSI is we were actually able to recover a lost retroreflector on the lunar surface using the Apollo system at Goddard. And so this is really exciting. It's significantly improved our ability to study center of mass and lunar interior. And again, I asked Doug if you're interested in learning more about this. Moving on to low-frequency radio science, and Jack Burns, and actually there's several presentations on low-frequency radio science in this session. This is something people are really excited about. Again, as I said, on Earth, we're limited by the fact that our own ionosphere becomes fully opaque at around 10 megahertz. Even above 10 megahertz, radio emission is strongly distorted and disrupted by our ionosphere. So it's very hard to form a precision image of the universe at low frequencies. A final setback, even if you're willing to accept crude imaging, is that frequencies of, say, 10 to 100 megahertz are unfortunately where we do a lot of our television broadcasting and digital and analog FM radio stations. So our skies are full of human interference in these frequencies that prohibit us from trying to detect weak signals at low frequency radio. People have known for decades that one way to address this and be able to make these observations is to get up into space, either with a platform of spacecraft, or better yet, to get into an orbit around the moon so you can use the moon as a shield, or ultimately to get on the far side of the moon and make observations. And so there are going to be a bunch of talks in this session on the different science you could do and the different observational techniques people have been working on. Let me just highlight a couple of them. So we have one concept that emerged from the work on Lunar is called the Dark Ages Radio Explorer, and there's a paper by Jack Burns that was published last year in Advances in Space Research on DARE, so I won't go into it in great detail here. And Jack has a talk about early prototyping work for DARE in this session, and there are several talks on the theory of the Dark Ages. But in a 1-minute summary, you may be aware of the cosmic microwave background, the idea being that after the Big Bang, as the universe expanded, it cooled off, and the cosmic microwave background is the last surface where you see strong microwave emission from the explosive remnants of our Big Bang. Beyond the cosmic microwave background, at later times, after the first 500,000 years or so, the universe has cooled off so much that we can no longer detect that direct emission from the cosmic microwave background. And in fact, the whole universe goes completely dark. And there is a gap of about 500 million years that we call the Dark Ages, where there's no intrinsic emission that we can detect from the universe. And you just have to wait, and then you can see the first galaxies, the first quasars, and the first stars begin to produce emission. So until we can detect the Dark Ages itself, we really don't have a sense of what's going on in our universe. And this is a really important period because this is where all the structure begins to form. This is where the sizes of galaxies, the number of stars, the organization of the universe,
about a minute left, Justin.
Oh, sure. That we see today takes place. So Jack and everyone else will get into the details, but it turns out before those first stars turn on, there's very weak emission that could be detected in what's redshifted now to very low frequency radio. And so there's a signature that we should be able to detect of that early formation of structure in the universe. And we think we could detect it at the moon, either with at first, a simple telescope orbiting the moon, and DARE is an example of that, that would just detect the global signature of this initial structure formation in the sky. And then the follow-on, and DARE is something that could go into Orion in one of the test flights, for instance. Jack will have plenty of information of this. But beyond a lunar orbiting mission, and this is my last concept, and we've already talked about this a little bit, are these ideas for arrays being operated on the far side of the moon. And there was a recent publication in 2013 laying out a concept for a lunar far side mission that would combine exploration and science. And so Jack is going to talk about both this and early prototype demonstration that just took place, which was really exciting, using the International Space Station and an astronaut on the space station to remotely operate a rover and deploy an antenna prototype. Now that antenna prototype was on the surface of the Earth, but we think we could use the same technology to build an initial array on the lunar far side. So, you know, I've just given you a very brief, I'll just skip to my conclusions, a very brief sense of some of the science that's enabled by exploration, but I think that also enables exploration. Studies of radiation, radio emission associated with solar activity, general tests of relativity and measuring the core structure of the lunar interior using laser range finding, and measurements of the early universe and of the sky and low frequency, both enabled by human exploration and possibly a very exciting initial activity for a human mission to the lunar Lagrange points. I'm happy to answer any questions, and if you're interested in all of this, I encourage you to go to the next session where you can learn about all of this in great detail. So thank you very much.
Thanks very much, Justin. Wonderful talk. I just love this stuff, as Jack will tell you. Really, really cool stuff. We are not going to take any